So shall we begin? So I want to introduce you Andrey Losev. Well, he has a lot of affiliations, let's say, from ITEP. Now, and we have a physical talk today. So welcome. I ask everyone to switch off your microphones. So,
why to switch off microphones? It's better if people would put.
No, well, when they need to ask, they will switch it. Otherwise, well, there are problems with quality. Okay.
Okay.
Welcome.
Okay. So sometimes the board could be out of focus. Please let me know. In this case, I'll have to reload. Video, it's several seconds. I would like to devote my talk today to the seminar that happened in Moscow 42 years ago, when smart people were telling to my friend that the proper physics should be described using homological algebra. Okay, and I'll try to show that in some sense it is realized. And
hello, Andrey Semyonovich.
Oh, hi.
Hi.
Vladimir Nikolaevich, don't interfere, please.
Okay. And here, so I can talk about different subjects, but today I'll try to talk about how main objects of physics, namely space-time, field. Do you see my writing?
Yes, we do. At least I do.
And also equations of motion could be united in a single concept. And it would be the first part. And the second part would be this is a general scheme. It would be interesting to get not some equations, but equations that describe our world, namely Young-Mills equation, Dirac equation. And I will show how this is done in modern physics. And we will see some technique of homological algebra here. Okay, so it's a plan, and I'll spend like 1 hour explaining this, and later on I'll try to answer your questions. So I'll try to explain why we as human beings and the rest of our world is actually built out of fluctuation of multiplication table. So it's a slogan, and it basically goes as follows. So space-time would be considered not as a fundamental concept that is given from the very beginning. Space-time would be considered as a infinity structure. So should I explain what a infinity structure is? Or a infinity algebra?
That yes.
So I'll recall that it's better to explain it in pictures. That you have operations with oriented inputs and one output. So this operation is mu3. It has two inputs, one output. And I put here the ribbon line in order to show that order of operation is important. So, and all these operations are called to form a infinity structure if they obey quadratic relations. I'll write down the simplest. Mu another mu. With quadratic relation, I have to take a sum, and it should be equal to 0. So this equation is known as simplest one, associativity equation. So solution to associativity equation, or in other terms, a infinity structure, is space-time. So there are really a lot of solutions to these equations. And there is a kind of the gauge symmetry on the space of these solutions. Actually, to understand the symmetry, it's better to recall that these operations could be formed together in the non-commutative vector field. Etc. You see, here T are free non-commuting variables. And then this associativity equation is basically a condition that this vector field is homological. A infinity structure. So you see, v square equals to 0 means that we are already in the scope of homological algebra. So we are not used to this equation, but we used to some linear part of it. It means that v is kind of differential. So it's something more complicated than being a differential. But in spirit is like this. It's called homological vector field. And when we have such solution to this equation, we can do what? What we do with vector fields? We have diffeomorphism. So the symmetry of this equation is of course like this. Lie bracket between v and u So this is a symmetry and U is a parameter. So the space of worlds is the space of this V homological moduli, this diffeomorphism. Okay. And in particular, we have the moduli space of solution. It is something. However, here we have an interesting subspace. It corresponds to commutative multiplication. It means that Vi, J1, J2 are structure constants of commutative associative algebra. And I depicted them as this line in the moduli space. So these are spaces, but it's not enough to have space, empty space, to get the world. We need to populate it with something. In old days, having space, people had to invent what to put on it. These things were called fields, and how to write down equations of motion. And since people know that everything comes from the gauge symmetry, so fields, equation of motion, symmetries, everything. However, it turns out that now we do not need to invent it. They are coming automatically. Namely, so this is the moduli space of A infinity algebras. We consider just vicinity of the empty spaces. So we consider V being V0 for space-time, plus fluctuation. And we call this fluctuation delta V. Now we would like to consider this fluctuation small, and let us see what can we say about delta V such that the total V is still an A infinity algebra. Of course, we will get Maurer-Cartan equation. So actually, it's better to put here not this type of bracket, but a proper bracket. Here is called Gersten-Haber bracket. So, okay, we have Maurer-Cartan equation, and we can study it perturbatively. So first we study linear equation, and then we will impose nonlinear part. Because I told you, delta V is considered as being small. So first thing is linear equation. Of course, moduli. Delta V is equivalent to delta V plus V naught U. So this thing is known as Hochschild cohomology. So fields are Hochschild cohomology. Of a infinity structure. So if you have an arbitrary infinity structure, it's hard to find its Hochschild cohomology. However, there is a well-known theorem of Hochschild, Constant, and Rosenberg that says that if you consider not arbitrary infinity structure, but space-time that is commutative associative, then for space-time Hochschild cohomology are just polyvector fields. On X space-time. So this is where the fields come out as fluctuations of the space-time. And it's clear where in the space of all non-commutative vector fields. Okay, so we solve this. And of course, I need to denote this fluctuation somehow. I call them P. P are polyvectors. Good. Now, I have this abstraction. I restrict it to polyvector, and I get the fundamental equation. And this is Schouten bracket. The natural bracket that you have on polyvectors. Would there be vectors, you will have Lie bracket. On polyvectors, it's a Schouten bracket. And this is universal equations of motion. So people also know this equation as Batalin-Minkowski equations. Actually, classical Batalin-Minkowski classical material chemistry equations. So here I would like to stop for a little bit and ask, is it clear what I am saying? Maybe
if you have questions, don't hesitate to ask.
exactly. You see, I am explaining very simple things. However, I am not writing complicated formulas. I am not writing complicated constructions. I just explained in 20 minutes how space-time, fields, and equations are unified in a single framework. It is simple, however, it's a bit unusual. So let me ask Joseph, what would you think about this unification?
What do you mean? Well, by the way, does this mean that Batarin-Vilkovitsky equation defines something like a Poisson structures?
So here Poisson structure is canonical. So these are BV equations on the canonical BV manifold.
What do you mean by canonical?
Pt star of y. So P is, so when people use P, it means that they are Russians, because Russian people, instead of saying shift of grading by 1 moduli 2, write this P. So if you have any manifold Y, T star of Y has a symplectic structure, traditional, conventional. Pt star of Y have odd symplectic structure. So functions on Pt star of Y are, of course, polyvector fields. So functions on T star of Y are tensor fields that are not that interesting. Functions on the Pt star of Y are polyvector fields. Functions on the Pt of Y are differential forms.
A comment on notation. Pt star means that we consider T star as a supermanifold with
yes, this is a super. Yes, that's why I'm trying to comment.
Not everyone knows this.
Of course,
this notation.
yes, exactly. That's why I am always asking. So please ask question, because actually the problem is in notation. So I will need it. So suppose you have a manifold Y with coordinates yi. If you have T to Y, it typically has coordinates yi and let me call them Ti. So Ti are coordinates in the fiber. This is not that interesting. It's much better to consider Pty. It means that these T's would be replaced by odd coordinates psi. And functions on Pty are differential forms. I can equally call it Fi. Fij, psi I, psi j. I will use it, that's why I'll explain this too. So this function is equivalent to the collection of objects f, fi, fij, etc. This is anti-symmetric, and that's why these are differential forms. In this notation, the DRAM operator is a vector field. So here I explained what PTY is. But now I'd like to explain not just PTY, but PT star Y. So star means that I dualize coordinates on the fiber. So PT star Y has coordinates yi, theta I with the lower index. Functions of yi, theta I.
And thetas are odd, yes?
Odd.
Y are even and thetas are odd.
Because of this P. So this is capital Greek P. So if you come from the Western school, you would say this. It's the same. So here we have function plus something with the upper index plus something with two upper indices plus etc. So a field with antisymmetric upper indices are called polyvectors. This is a vector, this is polyvector. So all these are polyvectors. Now let me comment on the Schouten bracket. If you have polyvectors, you have an important operation, divergence of polyvector. I will write it down in coordinates. Let me explain why I call it divergence. You see, I am doing linguistics at the moment. So, would it be a vector? Would be DIFI.
You mean sum?
Of course. It is something non-covariant, of course. Of course, it has another interpretation. So for a vector, we can say that if there is a top form on Y that I call omega, then I can consider LP omega divided by omega. It's exactly the divergence of the vector field P. So for omega equal dy1 dym, you get this formula. So that's why what I wrote here is a continuation of this formula to polyvectors. That's why it's divergence. Of course, this operator is not canonical. It depends on the choice of the top form. That's why this operator was not studied in classical times in the middle of 50s, where people were trying to understand covariant calculus and differential geometry. What are the natural structures? Okay, so here let me advocate the so-called Batarin-Vilkovitsky master equation. Batarin-Vilkovitsky master equation is the following. You take H that belongs to, that is coordinates on the formal disk. You study this object and you ask.
Andrey, sorry, this is P. This is our bivector. So
it's polyvector.
And how should I understand this notation? What should I do?
So polyvectors, being a function, could be multiplied.
In external way.
Yes, in the object.
So we just formally write down exponent. Okay, and the sum will be finite. Yes.
So let me do it as follows. Let me apply this thing. Consider H being not formal. Compute and then localize at 0. So let me consider this object for a moment. Then I have two derivatives here. So it's easy to see that this is equivalent to divergence of polyvector plus P and some operation here. It is shoot and bracket. And this gadget is known as Batarin-Vilkovitsky master equation.
Andrey?
Yes?
I think it is now called main equation, not master equation.
Main equation. It was called. Okay. Let us call it main. Maybe they call it master in Russian notation. Okay, main equation. Okay. So you have this equation. And then in the classical limit, you get this Schouten equation. And this is quantization that I am not going to talk about right now. So I am thinking about classical theory at the moment. So this, how this equation comes out from Batarin-Vilkovitsky approach. However, I try to explain that this equation, that the polyvector is homological. You see, the meaning of this equation is that polyvector is homological. So it determines the differential on Batarin-Vilkovitsky space. So this thing is derived from the concept of AN structure. So Batarin-Vilkovitsky postulated this equation from this construction. I somehow derived this together with the space. In Batarin-Vilkovitsky framework, the space was given. I considered everything as a unified concept. Okay, that's why it's good and important to study this object. Now, let me try to show that this object can already contain something physically interesting, like Young-Mills equations. Actually, I will find super Young-Mills equations that are even better. Okay? Once again, I have this polyvector. Then I want to expand it once again into the background polyvector plus fluctuation. And I play the same trick once again. So this would be, for me, specialize. Let this be not polyvector, but homological vector field. So what can I take as a homological vector field? I need to specialize further. You see? I have several choices. Choice number one. Take as PB something like psi I d over dyi. Then it would be something like the RAM. And the theory that I could get out of it would be as a linear level something like so moduli omega equals the RAM of epsilon. So what can I get out of this? Something simple like Chern-Simons. But it is not what I am going to get, because it's not that physical. I don't want Chern-Simons. I want something better. I want actually super young Mills. So it means that I have to look in the space of homological vector fields to find an interesting homological vector field. And interesting homological vector fields, such that we will get something that looks like our world, are very rare. Very rare. And however, there is a very good find. It was not mine find, but people found it many years ago. Very special manifold. So this manifold is R10 times spectrum of you see, it looks crazy, but that's what actually happened.
Well, but why?
Why this?
Yes.
The only explanation is that I know that people studied many homological vector fields, and all the time they found something very simple or very trivial like Chern-Simons, and this does not look like our world. In our world, we have the Lambertian equations. So we would like to have something like the Lambertian equations of motion. Not flatness of connection. If you have a flatness of connection, you don't have particles. We don't have matter. You don't have anything. So mostly, so when you do it in general position, you get Chern-Simons like theory where you have flat connections, and okay, perturbations of flat connections do not look like waves that we have in our space. They do not look like light, you see. We don't want conditions like flatness of connection. It has no waves. We would like to have a very special case where we actually have waves.
Andrey, just a minute. You say what we don't want, but what do we want?
We want young Mills or Maxwell. We would like to have.
We want math. Okay.
We need Maxwell equation. We need to have light. So it will turn out that Maxwell equation would come together with the Dirac equation in a single package. Okay? It's a bit surprising, but from this framework, it is done like this. And if somebody will find other interesting solutions, it will be very interesting to see. You see difference between what I called physical. So in physical solutions, you have waves, the Lambertian equations, particles, everything. In formal, that are called mathematical equations, you have flat connections. No dynamics. So let me come back to this diagram. So these were spacetimes. here we see fields. Now look at the looking glass here. Fields are polyvectors. Pick up a polyvector. Look in the vicinity of this polyvector. You can even have here differential equations, but these differential equations would be typically differential equations that describe flat connections. Nothing interesting. However, there is very particular, I try to write it in blue, very particular place and very particular homological vector field, such that in the vicinity of this homological vector field, we start to have something interesting. And all the rest is just not interesting. So it's, you know, it's like universe where we have a lot of stars. But, okay, stars have planets. But on most of these planets, you do not have life. Conditions are not good for life. However, there are rare stars where you have rare planets where you can have life. And we are interested in something like life. That's why I am not studying the very general case. I study something very specific, where you actually have life, where you actually can get this interesting dynamics. And once again, it's homological. So, very special supermanifold, R10. And here is the spectrum of very special ring. These are polynomials on lambda alpha and theta alpha, where lambda alpha are spinors, actually left spinors of SO10. So alpha goes from 1 to 16. Very special, very crazy manifold. And then you need to consider the coset. So here is ideal generated by this set of quadrics. So they are quadrics like this only in dimension 10 moduli 8. So to have these quadrics, you need to have pairing between left spinors and left spinors. Sometimes there are right spinors. You need this pairing to be symmetric in lambda. So there are not so many choices. However, in dimension 10, you have these quadrics. So you impose this quadric condition, 10 equations. And what is more interesting is that these quadrics do not form a regular, in terms of causal, sequence. It means that they do not intersect transversely. They intersect in a very crazy way. And exactly why they intersect in the crazy way, we are getting something interesting. You see, once again, very special space. Very special space. And now I'll write down differentials or homological vector field. It is plus it's not the only homological vector field that you can write. However, such field exists. Let me call it Q, pure spinor field. You might say, oh my goodness, how can I get here? So when you try to square this homological vector field to check that it's homological, this is homological because it's like a Joule differential or odd ram, depends how you call it. This also square to zero in the standard fashion. Since these are anti-commuting, these are commuting. However, Q PS square equals to lambda gamma m lambda d over dxm. And this vanishes because of this ideal. You may also try, okay, something very special. Now, the question is, of course, to find cohomology of this. And let me explain, let me give an answer. Solutions to Maxwell equation and solutions to Dirac equation. Together. As a bonus, we have a supersymmetry that goes between them in 10 dimensions. If you wish, you can go down in dimensions and then you'll get Maxwell equations in dimension 4 plus n equals 4 supersymmetry. But I need to explain this. Once again, I have to play homological algebra. Now, when I would like to compute cohomology of this Q, I see that there is the first differential, and this is the second differential. So first, let me compute cohomology of lambda d over d theta. So these are functions on R10, because you see this does not depend on x, times very interesting object. It's a higher torsion between the skyscraper and the ideal generated by quadrics. And this is nothing but the Joule differential here. So, would you have Joule regular? Would be a Joule regular set? the torsion of this would be external algebra. And the second differential D2 would act as psi over d over dx. Once again, not interesting. We are coming back to Chern-Simons. However, there are good news. This sequence is not and that's why it has very peculiar cohomology. So what can we say about this cohomology from the general grounds? They should form representations of R10, of SO10, I'm sorry. So these guys, so here everything is invariant under SO10, because these are Gamma matrices. These are intertwiners of R10. So let me tell you the sequence. We have scalar, vector representation, spinor representation, another spinor representation, vector and scalar. So instead of 10 pieces, in the case of Cavil regular, we have only 6 here. So this is the description of cohomology of D1. Now, what this means, that we have a scalar field. We call it ghost C. We have a vector field. So it would be connection. We have a spinor field. This would be gluina, etc. This would be anti-gluina, anti-connection, and anti-ghost. Now we need to get D2 acting on cohomology of D1. So this is simple, and this is nothing but the gauge transformation. So we are not surprised that in connections we have gauge transformation. When we go from this 16 to this 16, what we get here? The first order differential operator acting between spinors. The only thing that you can get here is Dirac. Dirac operator here, gauge transformation here. However, there is one very specific field that I have not studied, namely this vector field. I have no choice to have a first order operator here. So when cohomology acts here, it misses cohomology. So D1 between 10 and 10 equals to 0. However, oh, sorry, D2. I'm sorry, it's D2 that I'm writing. It goes to 0. However, I have, since it's a bicomplex, I have the higher operation. It is D2 homotopy D2. It takes this 10 and it goes, it ends here. So D2 has its first order operator. This operator is of the second order. So being a second order operator, invariant under SO10, and also that is gauge invariant, and it's a property of induction of differential, second differential to cohomology. We have no choice. It is Maxwell operator. That is how we get the main result. That cohomology of this very special vector field is combination of space of solutions to Maxwell equation and Dirac equation. And the last thing that I'd like to say is that this differential commutes with supersymmetry. Minus gamma m. So not only we get so-called physical type of equations of motion, they automatically have supersymmetry. You see where we started from. We started from the very general concept. And this very general concept was the concept of A infinity structures. Okay? And what we were doing in the process, we are finding solutions and we take particular solutions and the vicinity of the particular solution. Then we are deforming inside this class and we are again taking this vicinity. So I think under the fourth iteration in the very special neighborhood, we are getting Maxwell and Dirac from the first principles. This is the message I wanted to give. So it's 1 hour and 24 minutes. So I am 4 minutes behind the schedule.
Okay, thanks a lot. Well, Andrey, well, for me, well, you several times told that we got supersymmetry, yes? And why is it so important? Because for me, it is not clear. Why it is important to have a supersymmetry?
It's not important. We just get it as a bonus. From this approach, we are getting it as a bonus.
Yes, and what? Why it is good?
I don't say that it's good or bad. We have something. We were not asking for it. The equation was not to get supersymmetry. The equation was how to get the Lambert equations of motion.
So it's just, well, it's just a sort of byproduct which is good, but it's not. It is not very essential.
Yes, it's not very essential. So
Okay,
it is byproduct of this construction.
I see it.
So in this construction we get super young Mills. So this theory is of physical type. Okay.
Okay.
But it also has supersymmetry.
Yeah.
Of course, it would be interesting to find other theories using the same line that would not have supersymmetry. But it's very hard to find such theories. You see, it's the point. And somehow it corresponds to the fact that in so-called string theory, people managed to construct superstrings, and they were not so successful in constructing strings. And so maybe this is related. I don't know. But what I definitely know is that there is this construction. And it's the construction that I wanted to explain from the very beginning to the very end. So in the beginning, I have A infinity. In the end, I have super Maxwell.
From infinity, only plane space time emerge, or also can be manifold like general relativity?
It's a good question, but it is hard to say. So what I know about this? I know that if you study not R10 times this, but very similar construction for R11 and also spinors, then, and it's not easy to find, you will get at the linearized level, here I'm considering linearized level, wave equations for 11-dimensional supergravity. You see? So it is possible. So if you have linearized equations for supergravity, most probably you will get a supergravity too. You see, because here, so what I was talking about right now, I was talking about linearized level. It's an interesting question how to put in interaction. It's possible to do this, etc. But I wanted to stress this point. So it's possible to get supergravity, and that's why gravity.
Okay. No question? No more question?
So it's a pity that I have no questions, because
Yes, yes, I have the same opinion. Yes.
you see, once again, so I actually had two main ideas. First idea, solutions to A infinity equations, if you put in a small parameter, lead to classical main equation. Message number one. Message number two. Among solutions to classical main equation, there is very interesting solution such that their fluctuations again solve Maxwell and Dirac. Once again, when you start with this Q, you don't even know what type of fields you will get. The fact that fields are vectors and spinors has to be calculated. So once again, first you calculate, computing this cohomology, the types of fields, and then by inducing second cohomology on cohomology of the first, you are getting equations of motion. So actually it's the same mechanism all the way down. It's continuous perturbation theory in homological algebra.
Yeah. Okay, I would like to make a comment. For me as a mathematician, of course, it looks very nice that physical theories come out from cohomological considerations. But for me, motivations are completely unclear. That's why I think this is the reason why you have not many questions. This is, to my opinion.
Motivation is to unify, is to have unified equations. Motivation is to unify the concepts of space-time and field equations.
I would not call it a physical, to my opinion. This is something, aesthetical motivation, but not. Well, it's my viewpoint.
Okay, so it's
not a physical one.
No, I think it is physical, because in theoretical physics, first you find a mental construction, and then you need to show that this mental construction that you find corresponds either to our world or to world that is similar to our world. So of course, the main idea is to change the setup. Idea is find new setup in physics such that it would lead to something sensible. So this is the motivation. Rethink what quantum field theory is.
Of course, you know better than me, yes, but nevertheless.
Oh, I don't know. We are on the equal footing. If we think about fundamental structures of the world.
Yes, as a mathematician, it's well, it's perfect for me. Yes, well, but well, my model of a physicist is Isaac Newton, who sits under an apple tree and gets an apple on his head, and he is motivated to explain why. This is, from my point of view, this is a physical motivation.
Okay, and here I have the same. I am like Isaac Newton. I have Maxwell equations. I need to explain, why do I have Maxwell equations?
Yes.
So, so Newton was also starting to think. So first, he had to think that apple falls. Then he started to think that not apple falls on him, but maybe Earth also falls on apple. And then he had to construct the framework of bodies and field and forces. And then he has to consider the general forces. So starting from the question why apple falls on him, he had to invent the scheme where you have Lagrangian. So would he do it consistently? Where he had Lagrangian, universal potential, etc. So most of potentials would not lead to apple falling on him. But he found a special potential 1 over R.
But we shall continue with you. Hmm?
Okay,
I'm sorry, can I ask
Andrey?
a question?
sure.
Yes,
Yeah, sure.
when you were saying you want to somehow unify fields and space-time, what you wrote in the very beginning when you, at the very start of your framework, is that you wrote V0 and dV, Gerstenhaber bracket, and if I remember correct, you just said it was equal to 0. You just throw it out and leave only dv and dv Gerstenhaber bracket, only the second part.
Yes, because mu0 is a solution to is not a general mu, so mu0 is a solution to equation of empty space.
So in some sense, it is our space.
Yeah. So
Do-
space time. So
Yes.
so mu0. So mu0 Gerstenhaber
Я ничего не слышу.
is some space. It could be some non-commutative space, but we are not that interested in it. But if it is commutative space, it's our space. Yes.
And what about the fields? So from what you said, I have had an imagination that fields and this thing are commuted with each other. So the fields are somehow fundamentally distinct from the space.
No.
No?
mu0 plus delta mu. mu0 plus delta mu.
Oh, I see.
Here, so up to symmetries. You see, actually, this fundamental symmetry becomes, at the end, the gauge symmetry of Maxwell. So here, on the linear approximation, we have this equation. And this is Hochschild differential. For any mu0, this is Hochschild differential. So fields, in general, are Hochschild cohomology. However, if we take very particular space, that is commutative associative.
So it is our choice. So
Yes,
that
it's our choice. We happen to live on commutative associative space. That's why we have very special.
To see our universe in a linear approximation as we see it. Okay, I see.
Yes, so it's very hard. Yes, in some sense, whenever we have a field, we are moving from commutative associative space somewhere else. Okay.
Okay.
Andrey,
Yes.
I think I'm not completely satisfied with your answer. I think you artificially by hand restrict your deformations to not deforming the leading symbol of your differential operator. You do not deform dd theta and ddx to something else. You just add to it a vector potential, which is zero order operator. If you try to deform,
you are absolutely right. If I'll try to deform it in different ways, I'll probably get gravity.
You get what?
Gravity.
No, you don't get gravity. I tried. You lose wave equations. In this approach, you need to do something more. For example, add the second copy of lambda and theta. Or you can go to 11 dimensions.
This I know. So.
But how do you explain that you are restricting yourself to very narrow subclass of deformations? Moreover, I can add high-order differential operators. Why are you not doing this?
You see, for me, let me tell you. So for me, I wanted to show that there is something here. Of course, I'm not studying the general. I want to show, you see, in this talk, I wanted to show that you have at least Maxwell and Dirac plus maybe something else. so here I was trying to explain that this appear. It's not the exclusive classification. So I actually wanted to show that something like Maxwell theory.
I see.
So it is not, of course, it's not the complete story. And when you say that, okay, in 11 dimensions, you get supergravity, and the proper reference here is Berkovits, Hof. I think it's Hof Berkovits or Berkovits. It's called something, quantization of the membrane.
They have to consider the membrane wall sheet theory. It has additional structures. It's not just Q square equal.
You see, already not only membrane, you see, already string has additional structures. Yes.
Right. So you need wall sheet theory. It's not just this. I think I'm trying to understand if it's misleading or not to think that everything is captured.
You see, from the general perspective, it should be that everything should be here, because there are no other fundamental equations for the space-time. So actually, I think that, you see, when I consider this, I consider it homological vector field. However, there are polyvectors, and there should be a theory on polyvectors. And the theory on polyvectors should be, at the very end, the theory of gravity. And I just don't know how to do it explicitly in this approach. But I'll try. You see, my aim here was to show you that something like our world can happen. It's not the complete story of deformation. Of course, the main issue is how to study all deformations. This differential is very particular differential. In some sense, picking up this differential is already a choice of what we can call the gravitational background. It's important to study deformation of this. So in other theories, not physical theories like this, but in general theories, like in so-called B model. Okay, you asked this question, so I need to tell you what I know about. In so-called B model, the analog of this is something like this. And when you study cohomology of this, you have holomorphic bundles. But you can study deformation of this differential. And here you have polyvectors, actually. And this is B model gravity. So flat connections, okay, holomorphic flat connections are deformed by polyvectors. And this mu Beltrami differential entering here is exactly the gravity field that is fixed here. However, it becomes dynamical when you consider moduli of this differential. So based on these ideas, I hope that in some sense, moduli of this differential would correspond to physical gravity. Okay?
Probably it will be interesting to use one thing that in general relativity there is Frenet transport and it expresses a second law of Newton. So maybe you can incorporate this also in your model.
So you see, a frame somehow goes away here. So so instead of frame transport, you see, maybe you can put in frame somewhere here if you try to work it not on the flat space. Okay, so let me try to speculate. You see, here is very strange thing, R10. So it's very special. The question is how to write down this on the curved space. So of course, it would not be about the metric. Most probably, it would be about so-called wild bind. So most probably wild bind would come out here. So let me put it this way. So here I wrote this crazy index M. Okay? So being an index M, it is just a representation of SO10. Nothing else. We cannot have XM. What we can have here is the wild bind, actually inverse, and D or dx mu. So this is how gravity can enter the game. And then you should also impose conditions that Q pure spinor depending on epsilon squares to 0. And here you will get some equations on E. And most probably something like gravity would come out of it. Because it's this field that is actually fundamental field of gravity. It's not metric. Metric is a composite field. So being a physicist, I say that these so-called binds are like quarks, and metric is a meson. And this is a fundamental degrees of freedom, and G metric is just an effective. So gravity is about E. Okay? And being about E, I see E entering here. It's already a piece of gravity. Then,
Andrey, may I have a comment?
yes.
So I think we did this exercise recently with my student, Denis Zavaleta, and it's very close to what you are saying. Our result is very close to what you are saying, except for we had to introduce 2 copies of lambda and theta. It kind of comes from type 2b theory. And if you do it with 1 copy of lambda and theta, I am almost sure that you do not get Einstein equations.
It's
It is just direct computation.
It's interesting. So you see, I never tried this, but could you send me the link to your paper?
I will send you a paper for comments. We are not finished yet, but what I said.
Okay,
sure.
so it means that that we are thinking in the same direction.
Yeah. Yeah, let's join effort. Yes. Yeah, it's quite interesting. It's basically you study singular Q manifold. This equation lambda gamma lambda equals 0 is really what it describes. It describes singularity of your manifold, and then you study the normal form of a nilpotent vector field in this near prescribed singularity.
Of course. So life is in singularity. So it's okay. There is philosophical reason that life is the vicinity of singularity. I don't understand in which sense commutative manifolds are singularity, but it's philosophical question. So let me assume that somebody would explain me why commutative spaces are singular, but I would be pretty happy to work around commutative such that it is supercommutative, of course. And it is this question that seems to be important, because you see, so-called type B gravity works with the single mu, single deformation of the single differential. Mm-hmm. And you say that here it doesn't work. It's very interesting to understand why. Because similar thing or strange thing happen in 11 dimensions, as you know. There are crazy formulas of, I forgot the name of this Swedish guy. Berkovitz told me, I'm always forgetting his, so he has very typical Swedish name.
Sederwall.
No, not Sederwall.
Sederwall, yeah.
Who wrote interaction between 11-dimensional particles. And this interaction is so crazy and so weird that it will be better to understand how it comes out. So actually this, so what I know, I don't know a lot, but I know something. So this is type B gravity, if you deform it this way. And this type B gravity comes from the type B topological string. If you do this. So type B gravity, and so what would happen here? It should be an analog of type B gravity. Then you say that physical gravity is not this. So of course I know that if you double the system, you will get the field theory limit of the string theory. Okay? Of so-called Berkovitz string theory.
Yes.
And then by tensoring to super Young-Mills, you get supergravity in 10 dimensions. So then it's an interesting question. How to relate this with the superparticle coming from 11 dimension when you do not double. Also, this is actually an interesting point of research. So when I ask you to send me a link, maybe you send me a link by chat.
You have Gmail, don't you? You have
Gmail. Yes. I have Yandex Mail. So in any case, I'll put my.
You know, Zoom has chat. Maybe you could put it there.
Exactly. That's what I opened already. You see, but to know and to do are two different things. Then let me tell you something else. So if you consider this differential, and if you localize it at some particular lambda, it will be exactly the complex structure on R10. And that's why this looks very similar to this. So many people think that in some sense, pure spinor construction is a version of B model. However, you cannot localize at fixed lambda because this lambda has a radical at 0. Okay, you can see it from cohomology. Cohomology are actually polynomials in lambda, and moreover polynomials of fixed degree, of restricted degree. So it means that everything is supported at lambda equals to 0. So it's actually very interesting. So have you received my email in the chat? Maybe I need to press send it to. Yes.
No, we can see it. It's okay. It did go through. IS Losev too.
Okay. However, this is for experts. So I was trying to give the general philosophy. So what I still want to stress is that so for me manifold itself seems to be a gravity. So if it will turn out that it's not like that, then it would mean that there are geometrical structures on the manifold that would not come from this multiplication table. It would be interesting. You know, I have an opposite proposal. An opposite proposal is that you should have not only one multiplication table, but actually two multiplication tables. And what we used to call manifold is a copy of the manifold and its complex conjugate. And then maybe we will get a doubling. I have a reason to think so based on bosonic string considerations. And if you would be interested, we can discuss it separately. Okay? Good? So the issue is that now we don't have organizer. So,
yes, Joseph wrote that he has to disconnect. So let me ask everybody, are there more questions?
So we can move anywhere from this. So since I was considered as a speaker, somebody has to take a role of the organizer and say that we can continue or do something else, meet somewhere. No, okay, let me take the role of organizer. So you have my
Okay.
email, okay? If somebody is interested, just write me and we can discuss some other topics. Let me make an announcement, okay? What we can discuss. Announcement is like this. Announcement. In bosonic string, I call it bosonic string. Geometry is given by the following data. Manifold X bar, not necessarily complex conjugate. Differentiations of X, semi-direct, extended by 1 forms on X, plus 0 forms on X. So this is a complex. This I call LX. It's also Lie algebra. Is given by. So geometry is LX tensor LX bar. Second, equation of motion for the geometry G is given by QG plus double bracket of GG plus maybe higher corrections. I can discuss this issue if somebody is interested in general gravity. So there is general relativity, and this is general gravity. So what's important here is that X could be a scheme. X doesn't need to be a complex manifold. And I can explain why this is gravity. So gravity is the Maurer-Cartan equation. I need to put it in the special color. No, I even put it here. Actually, this is the equation of beta function equal to 0. So I can try to explain what does it mean and how it works. Okay, so still we have no organizer. You see, like when you have a war, you should have somebody who says, okay, let us stop the fire, let us write the new peace treaty, capitulation, whatever, you see. And there should be a celebration.
Yes. So let us stop and celebrate. And thank you very much.
Okay, but you see, like in the war, after a peace treaty, you typically have another war. So now let us make a peace treaty, and you may write me, and then we will continue the war. Okay. That's it. So thank you everybody for listening.
Thank you very much. It was a very interesting talk and very, very interesting discussion. Yes, thank you. Maybe and what you said, maybe I wrote you, and maybe I don't know much, but maybe you can just shed light on something I don't understand.
Sure.
Thank you very much.
So goodbye.
Goodbye.